Elasticity and elastic modulus. The relationship between applied force and elongation is linear up to the proportional limit. Hooke's law is only valid in the elastic region down here. And what graph do I have here? We're plotting elongation versus applied force. This graph is based on a series of experiments for different materials. The elastic limit, which is right over here, right there, that's when the force is removed, the object will still return to its original length. So all the way up to there, as you apply a force right up to the elastic limit, the object will go back to its original length. The plastic region, objects elongated to this point will no longer return to their original length. They become permanently deformed. And finally, you don't see any data after this. Why? Because that's the breaking point. The maximum elongation is reached, and then it breaks. The elastic constant is experimentally determined from many trials involving rods of different dimensions and materials. This results in an empirical equation. A theoretical equation is created to explain a phenomenon, but it may have an undefined constant. Experimental data determines the constant leading to the empirical equation. This particular empirical equation holds only in the elastic region. Experimental data was fitted to Hooke's law. Hooke's law was a theoretical law, and it was found that the amount of elongation of the rod depends not only on the applied force, but also on its original length, cross-sectional area, and the material of the rod. The amount of stretch, elongation, and that's delta x over here, is proportional to the original length and inversely proportional to the cross-sectional area of the rod. So delta x is the rod's elongation, F is the applied force, A is the cross-sectional area of the rod, and x0 is the original length of the rod. E, right, that's the new term here, is a constant known as the elastic modulus or Young's modulus. It is a property of the material and is independent of the object's shape or size. And rearranging the top equation, this is what E, or Young's modulus, is equal to. The value of Young's modulus for different materials is presented in the table. And 1 gigapascal equals 1 times 10 to the 9th Pascal, where Pascal is the SI unit for pressure, and it is also equal to newtons per meter squared. Notice, steel has a very high Young's modulus and rubber has a 0.02 very low. Rubber will elongate more than mild steel for the same applied force. This equation shows that the elongation delta x is directly proportional to the object's original length. When the original length is larger, there will be a greater change in length. Another part of this equation is the ratio between the applied force and the cross-sectional area. That ratio is called stress. Since the object is being stretched, it experiences tensile stress. So stress will be sigma, force per area, or F over A, and its units are Newton per meter squared. Strain, or epsilon, is defined as the ratio of the change in length, elongation, to the original length. It is unitless because you have meters over meters. They cancel out. Young's modulus is then, well, here's our delta x. We solve that for E. Right, there's Young's modulus. F over A is sigma, and then delta x over x0 is epsilon. So epsilon goes in the denominator there. And we have Young's modulus is what? It's stress over strain. Now, what's the difference between stress and strain? Stress is applied to the material by external forces, where strain is the material's response to the stress. All right, so here we go again, stress over strain, or stress is equal to Young's modulus times strain. Strain is directly proportional to stress from materials in the elastic region. Find the Young's modulus of a material which halves in length when a force of 3,000 newtons is applied over its 28 times 10 to the minus 6 square meter area. We list the givens up here. And first we have to interpret, what does half mean? Well, since the material's length is cut in half, the change in its length will be, here's your change in length, it's the initial length minus half the length. So of course that's x0 over 2, but I just want to be a little formal there. So we're going to use Young's modulus equation, substitute in our givens, and here's the fun part right here. There's no actual numbers there other than the 2, but what we have is x0 is on top, then delta x is x0 over 2. So the x0's cancel out, the 2 comes up top, and we get Young's modulus as 2.1 times 10 to the 8th newtons per meter squared. And I just showed the other ways you could represent that, right? A newton per meter squared is a Pascal, and 10 to the 8th is not a gigapascal, but 10 to the 9th is. So if you move the decimal place over, you get 0.21 times 10 to the 9th. So it is 0.21 gigapascals. Find the stress of a spring which is stretched from its original length of 0.75 meters by 0.050 meters and has a Young's modulus of 13.5 gigapascals. We have our givens at the top, and we're going to combine the Young's modulus equation with the definition of what? Of what stress? Stress is F over A. So we replace the F over A here with sigma, and then we solve for sigma. Multiply both sides by E and divide by x0. And here's our expression for the stress. Substitute in the givens. And notice we had the gigapascals here. So that's 10 to the 9th pascals. And we have to work in pascals with the equation. And we get sigma is 9 times 10 to the 8th pascals. Find the strain of a 0.50 meter spring with a spring constant of 480 newtons per meter, which elongates when a force of 120 newtons is applied. Here's the givens. And notice we haven't said how much it will elongate, and it turns out we don't need that, even though the strain equation has the elongation right there. But we're going to use Hooke's law, where F is equal to K delta X, or delta X is F over K. Substitute that in. We're down here. So the strain is F over Kx0. Now we can substitute in our givens, and we find that the strain, or epsilon, is 0.5, and it is unitless. What is the Young's modulus of a spring that experiences a strain of 0.00030 and has a stress of 2.1 times 10 to the 6th newtons per meter squared? We use the Young's modulus equation, the version that has stress over strain, substitute in our givens. We have stress on top, strain on the bottom, and we get a Young's modulus of 6.7 times 10 to the 9th newtons per meter squared, or pascals.